So recall that if alpha is algebraic over some base field f, then associated with alpha we have a minimal polynomial. So this minimal polynomial which is associated with alpha, we denote it as m subscript alpha. So this polynomial is monic, so we chose it to be monic. It is irreducible, it is prime, and it is maximal. So the proof we showed was for prime, but that proof carries word for word to irreducible. So the degree of extension was precisely the degree of our minimal polynomial, and the base was 1 alpha all the way to alpha n minus 1 if degree of our polynomial was n. So degree of m alpha was n, then this was the base. So we also showed that the degree of such an extension e over f, so if the degree of this extension is finite, then this would imply that e is algebraic extension of f. So now we do some very important computations to show how do we actually get these extensions in practice. So say you want to get a root 2 adjoined with rationals, then you consider the polynomial x square minus 2 and over rationals, and you take the quotient, you get root 2 adjoined with rationals. So you see this is the minimal polynomial associated with root 2. Now you want to adjoin root 3 to this. You now start with this field. So notice that you're building it step by step. You start with this field, then you take associated minimal polynomial here. That's how you get root 3 here. So notice, because we have this irreducibility here, that's why we can't take both x square minus 2 and x square minus 3 at the same time and get this. So we have to go step by step because we have to take irreducible polynomials here. So this is what you get. So now say you want to adjoin root 5 to it. Again you take this and then quotient out by x square minus 5. Then you get this. So notice the process. From rationals you went to rationals adjoin root 2, then you went to rationals root 2 root 3, then you went to rationals root 2 root 3 root 5. So there is nothing special about first going root 2 and then root 3 and then root 5. I could have just started with root 5 by taking x square minus 5 here. So notice that our minimal polynomials, so our first stage minimal polynomial was x square minus 2, and then we had minimal polynomial which is x square minus 3, and the final minimal polynomial was x square minus 5. All these minimal polynomials, so this x square minus 2 rise in rational over x square minus 3, this also lies in here, but it also lies in a bigger field if you attach root 2 to it. Similarly, this also lies in this, or it lies in this. So the idea is that these minimal polynomials also lie in this base field which is rationals adjoined with x, and you construct these extensions inductively. And why I'm saying this is because this is the idea which we are going to use in our next proposition. So the proposition which we want to prove is this. Say L is an algebraic extension of E and E is an algebraic extension of F. Then L is an algebraic extension of F. So we have L which is algebraic over E and E is algebraic over F. Then we are saying that L is algebraic over F. So this is what we want to show. So to show the extension L over F is algebraic, we need to show that every element alpha in L is algebraic over F. So our strategy is that we pick some arbitrary alpha in L and we show that it belongs to a finite extension of F. So basically we want to show that you adjoin alpha to Fn over F. This is finite. So where Fn is some finite extension of F. So the idea is this. We want to use this theorem. So we will show that this extension is finite. So that means Fn alpha over F is an algebraic extension of F. So instead of E, we are now going to write Fn of alpha. So if this is algebraic over F, so in particular alpha will be algebraic over F. So notice that although we have an algebraic extension here, we showed in the previous lecture with an example that it is possible that this is infinite. But for every element alpha, we can construct an extension like this over F which is finite, and therefore we can use this result. So extension is finite, that means extension is algebraic over F, which in turn implies alpha is algebraic over F. So let us show the proof and show that this is possible. Now since alpha is algebraic over E, we have a polynomial like this which corresponds to alpha. So this is the minimal polynomial. So P of alpha is 0 and the coefficients lie in E. So alpha lies in L and we are saying L is algebraic over E. So therefore you have a polynomial like this and the coefficients lie in E. So since the coefficients lie in E, you immediately know that corresponding to every coefficient there is a minimal polynomial. So say your minimal polynomial corresponding to every coefficient, say let us put it as MCI. Now this minimal polynomial will lie over field F. So this minimal polynomial lies in f of x. Just like this x square minus 2 lies in rationals adjoined with x, and this x square minus 3 also lies in rationals adjoined with x. And the idea is that now we will force this x square minus 3 to lie in a bigger field. Similarly here, this MCI, we will force it to lie in a bigger field. So if it lies at the base field F, it obviously lies if you enlarge this field F. So let us do this. So you start with this coefficient C0. So C0 over is in E. So C0 is in E, and E is algebraic over F. So you have f of C0 over F is finite. So basically you say C0 is algebraic over F. So there is a minimal polynomial associated with it, which is MC0, and the degree of this extension is degree of this polynomial, which is finite. Now let us start inductively constructing the fields. So F0, you have adjoin C0 to F. Then F1 you construct by adjoining C1 further to FC0. So this is basically to F0 you adjoin C1. Similarly you can construct F2. F2 you can take F1 adjoin C2 to it, which is same as FC0 C1 and a C2. And then you have Fn, which you construct from Fn minus 1 Cn, and you construct it like this. So notice that every time you have a finite extension. So just pick up something, just let us pick up C3. So if you pick up C3, you have a minimal polynomial associated with it, which is MC3, which is of finite degree. This minimal polynomial lies in f of x, and therefore this f of x obviously lies within another field, which is f. Now this is C3, so you have elements C0, C1, C2, C3, x lying in it. So this lies, you can say that we want to go from f C0, C1, C2 to this field. Forget about this x right now, you want to go from here to here. So obviously you have the C3 here, so you have the minimal polynomial corresponding to it, which is MC3. So your degree of extension is, you have F2 here, you have F3 here. So you have a finite degree of extension from F2 to F3, which corresponds to degree of this polynomial MC3. The same way we wanted to go from root 2 to root 3, you modulo out with the minimal polynomial corresponding to root 3. But now, although this x square minus 3 lies in the base field Q of x, you now consider it lying in rationals root 2 and x. So that's how we have it. So this is this degree of extension corresponds to the same as this minimal polynomial MC0. This corresponds to this MCN. And now once you have adjoined all the coefficients to it, you have constructed a nice base field f of n. This contains all the coefficients. So instead of Ci in E, so now you can say that all these Ci's lie in Fn, because you have constructed this Fn by adjoining all the coefficients to it. This is also finite, Now this is finite because our corresponding minimal polynomial is precisely this. All the coefficients lie in f of n, and p of alpha is 0. So this is finite, all of them, and these are finite because their degree of extension corresponds to degree of extension to the degree of the minimal polynomial. So everything here is finite. So now you use the Tower law. These two will cancel out, then corresponding these two will cancel out. This will cancel out the one before it. So you will have fn alpha over f remaining, which is finite. So similar ideas apply here, and you can construct a subfield of algebraic elements. So say you're given a field extension k over f. Then the elements of k that are algebraic over f, so elements of k which are algebraic over f, they form a subfield. So to see that, say you have two elements a and b and k, and both this a, b are algebraic over f, then a plus minus b, a, b, a inverse, they all lie in this field f, which is adjoined with a and b. And this you can see immediately that this is finite. So therefore alpha and a and b are algebraic. So this you can construct again like this: f a b over f a and f a over f. This will be finite because, again, take your minimal polynomials corresponding to a, corresponding to b. So this will be finite, and therefore this a and b are algebraic, and you can form a subfield like this.